Ever since we're introduced to trigonometry, we're told that it has to do with right angled triangles. And then all of a sudden, somewhere down the line, we're told that it really has to do with circles. And well, all of a sudden, we're dealing with circles on the coordinate plane. And well, okay, wait, what is going on? Well, the relationship between circles and triangles is a lot simpler and a lot more intuitive than it would appear at first sight. And to understand this better, let us first consider an ordinary set of axes and a point. Our goal is going to be to determine the location of this particular point. Well, given what we already know, we know that it has an x coordinate and a y coordinate, and its location can be expressed in terms of these two quantities as x comma y, right? This is pretty obvious, so where am I going with this? Well, all right. Let us first leave aside what we already know and imagine ourselves in the following scenario. Okay, we're in the middle of the desert, right? We have no food or water, and our only hope of survival is to find an oasis. By our good fortune, we happen to bump into a Bedouin gentleman. And when we ask him for directions, well, he isn't going to tell us to walk 3 miles east and then 4 miles north to reach the oasis, is he? No, he is instead going to tell us to walk 5 miles in, well, that general direction and then point somewhere. And, well, that gives us our location. It naturally follows. Why can't we do that over here? And the answer is we can. So let us consider our point of view to be from the origin. We need to know how far away this particular point is in order to ascertain its location. So let's draw a line and let's measure the length of this line to be our units. Right? Now that we have our distance, we just need to know in which direction to walk to reach this particular point. And well, whenever we're dealing with directions, what is the most intuitively obvious way to express it? Angles. Which means if we know how far to walk and the angle to the x-axis at which to walk, we will have determined the location of any given point on the xy plane. Amazing, isn't it? And we can represent this as r comma theta, which is in fact known as a polar coordinate. This system of coordinates, polar coordinates, is intrinsically linked to circles, triangles, and trigonometry and will prove key to understanding the relationship. But all right, one step at a time. How do we get from here to here? Well, okay. In order to go from this already familiar so-called rectangular or Cartesian format to this novel polar format, let us take both of these formats and then superimpose. Wait, hang on a second. All of a sudden, we find ourselves in a very familiar scenario. We have a right angled triangle, we have the lengths of all our sides, and we have an angle. Everything about this screams trig. So if we apply what we already know, we will find a way to convert these obscure polar coordinates into the more familiar rectangular coordinates. Y over r is sine theta, therefore y is equal to r sine theta. Similarly, x by r is equal to cosine theta, therefore x is equal to r cosine theta. And by plugging these values into our typical x comma y rectangular format, we get a rectangular representation of a point for which we only know the distance from the origin and the angle at which it lies. Brilliant, isn't it? Well, okay, you might ask, all right, now that we've established a relationship between polar coordinates, rectangular coordinates, and trig, what does this have to do with circles? To understand that, let us first draw a circle and let us consider a point lying on that circle. Well, the defining property of any circle is that all points on that circle lie a certain standard distance away from its center, the radius. And in this case, well, the center is in fact the origin. And let's consider this particular point. It lies r units away from the center, where r refers to the radius of the circle. And again, what distinguishes this point from any other point lying on the exact same circle? Nothing except the angle. And we can just apply what we already know, and we arrive at a conclusion that the coordinates of this particular point in rectangular format are our cosine theta and our sine theta. All of a sudden, we have gone from absolutely nowhere to an obscure new coordinate system to linking back to trigonometry and then coming back to circles. But it was a lot more intuitive than it sounds, wasn't it? Here we have an absolute clear relationship between circles, triangles, and trigonometry.